Alrighty guys, we're going to get started. I'll do a couple of quick announcements at the very beginning. It's just like real school, everybody gets real quiet as the teacher gets ready to talk. Class, I should have one of those videos from that old TV show. The bathroom's in the very back. There's some hot tea that the Athenaeum's provided, so you can grab some hot tea. And if you did not give us your email when you're registered, please make sure you write your email down on the clipboard in the back. Last week I sent out a link to both Google Docs and Dropbox, which has not only the PowerPoint, but all the links embedded into that. So if you didn't get it, that means that we don't have your email. So you should have seen that in your, maybe in your spam folder, hopefully in your inbox. And I've already created the one for today. So anytime that you guys want to review this, you'll be able to. And Larry and I are Larry's here from NCTV, Channel 18, kind enough to volunteer his time to help film this. He's waving, I'm waving. He says, stop talking about me. We're gonna be filming this. It'll be playing on Channel 18 on NCTV. And we are thinking about maybe making a DVD out of this. So that might be something that we'll do too. And if people want it. And let's see, bathrooms in the back, you know where the exit is. Please make sure and turn off your cell phones. I'm gonna do my very best to talk loudly. If you can't hear me, just wave and jump up and down. We can take questions as we're going, and I'll try to leave a little bit of time at the end for questions, and I'm always happy to stick around if you have some questions afterwards. I brought some show and tell again this week, and there's going to be a movie here tomorrow night on wolves in China, so definitely check out all the Athenaeum's offerings. There's always something good going on here. And without further ado, we're going to get started. We have tonight and then 3 more sessions, one next week, and then the first 2 weeks in February. So I hope you'll join us for as many of these as you'd like. And I'll do a little bit of a review back and forth from week to week. I know I'm going quickly, but I will try to make sure that you guys get a chance to digest as much of this as you'd like to. So today we're going to cover, I'm using 2 different books actually today. This introductory book called How the Ocean Works, which is quite good, and then the Essentials of Oceanography. So I'm using a little bit of both of these books, and they can be rented online. You can actually download them straight to your device. You can buy them used. I still have not found mine at the fuel station. It's buried somewhere, but anyway, I'm using both of those, and all of this can be found online. So today we're going to be talking about what seawater is and learning more about the ocean floor. But one of the things I wanted to do is a callback, what we would call a callback in show business, to this slide from last week talking about the dimensions of the Earth. And one of the things that I think is most important is, you know, how big the ocean is. And we'll talk about this in different ways. But the average height above sea level is 875 meters, 2,871 feet on the dry part of the planet, on the part of the planet that's terrestrial based. The average depth of the ocean is 3,794 meters, so about 2.45 statute miles. The volume of livable space in the ocean is 100 times that of what's occupied by terrestrial parts of the planet. So later on in this class, we'll be talking about the carbon budget and how the ocean might save us, and certainly how it's been protecting us for a long time. And a lot of the things we'll be discussing tonight are relative to the globe as a whole. And the ocean acts as a thermostat, as a heat mover, as a giant convection oven. Without the ocean, we ourselves would not be alive. So this is what we're going to try to cover tonight. I've outlined that in red, where the ocean came from, ocean chemistry in the ocean basins. Ocean sediments we're going to cover next week, but we'll talk a lot about plate tectonics tonight. And that's one of the funnest things for kids. You guys might not know, but for a little while I was teaching at 3rd graders over at the elementary school about volcanoes and rocks, and they loved that. These are the other topics that I mentioned last week, for those of you who weren't here, that we'll be covering during the class, which include everything about the basics about our planet, the exploration and history we covered last week. We'll have a couple of sessions talking about the creatures that live in the ocean, the currents and how that interacts with the atmosphere. So we'll talk about the currents both in the atmosphere and in the ocean. We'll talk about coasts and waves, and then our use and abuse of the ocean with a finale on climate change. So without an ocean, without seawater, we would have no ocean. The ocean is made primarily of seawater. And we're going to talk first about water molecules, which are made of two hydrogen atoms covalently bonded to an oxygen atom. And most of the time when I teach, I always present information usually in three forms. I'll present it visually, verbally, and then I'll show you several pictures. So if you don't get this in just 2 slides, I'm going to show you a couple of pictures. Each of us learns in different ways, correct? So some of us really absorb it if it's written. Some are listening hard and absorb it through our ears. And then others need to have a picture. So don't fear if you see a lot of writing, there'll always be pretty pictures, which I need. And I'll repeat things a few times, and I hope that's not too annoying. Just let me know. Oxygen molecules have a weight of 16 daltons, and a dalton is 1/12 of mass of typical carbon. Carbon's actually used as the measuring block for the weight of elements, and if we were doing a whole chemistry class, we'd go into great detail, but you'll just have to trust me there that oxygen molecules have a weight of 16 daltons. The hydrogen atoms have a mass of 1 dalton each, so water is a total of 18 daltons. The hydrogen atoms in an oxygen molecule lay at an angle at 104.5 degrees. So they sit like a little tripod. And almost everything that water does is based on this weird little shape. And you'll see exactly what I mean in just a second. This creates what's called a tetrahedral shape, which causes water to have polarity. I'm sure you guys have heard about this. So it's got a charged negative end and a charged positive end. So it's always going to have that charge, and that charge actually controls most of the processes on the planet. The covalent bond means that the charges are shared. So the oxygen and hydrogen are more than just, acquaintances, they're buddies. They can't, in a hydrogen and a water molecule, they can't exist without the other one. So they're sharing constantly these charges. And it's a very stable molecule, and there's all kinds of properties of water that we're going to discuss that are based on its stability. So water molecules are extremely stable. If anyone's ever tried to do anything like a fission bomb of hydrogen and water and try to create hydrogen from that, it takes a fair amount of energy. Oxygen is very electronegative, so it's got 2 negative charges. This means it has a higher affinity for electrons, so it's always trying to grab electrons. So the oxygen end is negative, and the hydrogens are 2 little positive guys sitting out here with a positive charge on each end. This causes what's called a dipole and makes water a polar molecule. There's plenty of nonpolar molecules, but water is extremely polar, which means charged. I don't know where I'm getting feedback, but sorry about that. The water molecule, here I say it's pretty much the coolest thing ever. There's a whole link here that goes into great detail about it. It's really a fun link. But here are some different visual versions of what a water molecule looks like. Here's that 104 degree. Now obviously we're zooming in on a molecular level, on an elemental level. It's not like you can look at a molecule of water without some help from a pretty high level microscope. Here is the oxygen molecule with its 8 electrons. It's sharing 2, 1 each with these little hydrogen buddies. Here's another example of it. Here's basically the electron cloud, because we know that the electrons aren't actually single entities. They exist in in a cloud at any given time. So a lot of times elements are described in this way. Here shows a whole bunch of hydrogen bonds occurring between oxygen to hydrogen, this hydrogen to this oxygen. It's a little bit, I'm trying to think of this in a PG manner. Anyway, it's just a big party, right? So this shows you why water likes to bond together. It makes a carpet or a mat of positive and negative charges, and so if it's anywhere near another water molecule or another polar molecule, it's going to want to grab onto that. And these strong charges will also grab onto ions, and we'll talk about sodium and chloride and other ions, but this chemistry is why we're alive. Next slide. Water's still very amazing. The chemistry in that polar molecule and the shape of the molecule means that water can do a lot of things that other liquids at that temperature cannot do. For one thing, water is one of the few things whose solid form is lighter than its liquid form. Most things in the liquid form are going to be less dense than the solid form. As water actually becomes ice, all of those hydrogen ions, and they basically, if we were all up on this stage, and it would be pretty fun actually, and we had like little hydrogen ion things, and we kept our arms at 104.5 degrees, and we all were just bouncing around off of each other. We could only get so close to each other, right? You know, because our arms would be sticking out at 104 degrees. When water turns into ice, it actually changes that angle, and it pushes all of the elements apart and lowers the density. So everything stays further apart and makes it float more. So it changes the structure. Water should boil, that's why ice floats. So if you're on the ocean and you see something floating, that's a good thing to jump on. Water should boil at much lower temperature. The hydrogen bond keeps this from happening, so it's hanging on to each other, and it doesn't want to turn into a gas. So it's got such a strong affinity for each other that it doesn't want to change state and give up latent heat. This allows water to be a liquid at a wide range of temperatures. So this is just showing the boiling point from 100 degrees C down to -100. This is the estimated boiling point of water in absence of hydrogen bonding. It would boil all the way here, but in reality, it boils right at 100 degrees, way up here. See the difference between it would boil at -100. We've achieved this liquid planet because these hydrogen bonds keep water from going into the gaseous state. Here is hydrogen fluoride, ammonia, hydrogen sulfide, a lot of other hydrogen-based elements, and they have boiling points that are much, much lower. The heat capacity is the ability of something, a specific heat capacity or specific heat is the amount of heat energy required to raise something 1 degree. 1 kilogram, or 1,000 grams, which isn't all that much, of a substance by 1 degree Celsius. So 1 kilogram of water, which is 1,000 grams, which is actually just 1,000 milliliters or liter. It's not that much, about this much. We could all easily drink a kilogram of water, hopefully. It takes quite a bit of energy to change that by 1 degree. So what we do is we look at the heat capacity, and why does this matter? Well, our entire planet has this warm, well, it's hard to believe right now in winter, but you know, a warm envelope of livable space because this water is holding on to the heat. So gold has a heat capacity of 130 joules per kilogram. Doesn't take that much heat to melt gold. Liquid methane, 2410 joules. Joules is a measurement of heat per kilogram per degree Celsius. Liquid water is twice that of methane. Air is 1/4 that of water, and then granite is closer to air. So it takes more energy to raise, and you guys, when you think about this, if you had just a room, it's much easier to heat a room. You don't have to introduce too much heat. It takes a long time to heat up water or to cool water, but once it's hot or cold, it takes a long time for it to go to any other temperature. It's very stable, right? That's why we use these ideas anytime we use a boiler. We put a lot of heat into water and then it retains that. Anyone that's sat on a granite, if you go up and you've got a cup of water, granite, air, all at the same temperature, you'll be able to just touch these items and get an idea of how much heat, what their heat capacity is. I debated about leaving this in here because it's kind of a high level concept, but you guys look pretty smart, so I think we can handle it. And everyone's like, oh, you're looking at another room. That's not me you're looking at. And some of these things, don't worry if you don't absorb it all. I've had to teach this 3 or 4 times, and I still learn something every time from my own PowerPoint. But the redistribution of energy across the Earth's surface is accomplished by sensible heat flux. And all of these concepts actually apply when you're heating your home, when you get into a car. Once you start thinking about these concepts and you walk around on the world, you'll understand kind of how things are working. So we redistribute energy across the Earth's surface through sensible heat flux and latent heat flux. Sensible heat is the amount of innate heat you have. It's the energy associated with the temperature of the body. So if you're a warm-bodied creature, you've got X, Y, Z, you've got X amount of sensible heat. It's greater in a warm body than a cold body, so it's relative. Warm water that's heated in the tropics and cooled in high latitudes brings sensible heat poleward. So we're gonna talk about this in many different ways, but the sun's beating down on the equator, right? That warm water is gonna flow to the poles and it's gonna give up that heat. Latent warm winds carry sensible heat from one place to the other. So if you create heat, you've got a fire, right? That fire is coming to you, it's bringing sensible heat to you. And it feels sensible, it feels like that's good, we like that. Latent heat is kind of the heat that's trapped in things. And it's energy associated with changing the phase of a substance from a liquid state to gas, from a liquid to, if you go from a liquid to a solid, those are phase changes. Changing the state from a gas to fluid or fluid to solid or the reverse. The enormous amounts of latent heat involved in evaporation and precipitation of water make the hydrologic cycle a central player in the operation of the climate. It takes so much energy to evaporate water and then put it into clouds and then rain it out. That energy is what translates heat in the atmosphere. And we'll have a whole class where we're talking about atmospheric heat exchange. And we'll talk about the oceans. But the oceans are basically, you know, a combination of a big convection oven. It's heated, as we'll find out, from tectonic action underneath inside the earth. So we've got magma, lava, we've got this warm ocean, we've got moving clouds. All of this is this giant merry-go-round of motion, and it's carried by energy. Without this energy and this heat, things wouldn't move. Wind and ocean currents are movers of heat. The energy stored is the latent heat in the atmosphere. In the surface of the water, it's stored as sensible heat. Atmospheric and oceanic circulation share the task of heat redistribution about 50-50. So now think of it, if we didn't have an ocean or atmosphere, the Earth, we would just be like boiling hot at the equator and freezing cold at the poles, right? Because nothing would be happening. Nothing would be redistributing that heat. If in your house you didn't have convection currents because you had an atmosphere, if your house had no atmosphere and you didn't have any liquid in your house, you would have one part of your house right by the furnace would be boiling hot and the rest of the house would be freezing cold. You've got to get convection and currents to circulate that heat. In this case, ocean and the atmosphere split that duty 50-50. Even though transfer of heat by moving water and ocean currents is much less efficient, there's a whole lot more ocean. So the masses involved are much greater in ocean currents than in air currents. Part two, heat has to be moved. Heat's hitting the equator. You've got the sun facing straight down on the equator, good part of the year. It's more directly impacting the equator. Equator is a little bit closer to the sun. So heat has to be moved from the tropics to the poles, and it's hard to believe if you live by the poles, but we are getting some heat from the tropics. Otherwise, the tropics and the poles would be in trouble. So the higher latitudes would be anywhere from the equator up to 40 degrees, and then the very high latitudes are beyond the 40th degree, have a heat deficit. So there are areas with excess heat and areas without enough heat. The heat deficit refers to the fact that these regions receive more heat is radiated back than they keep in. Heat excess means there's more energy coming in than they radiate back. So the climate is like, you know, redistribution system that redistributes this heat throughout the entire world. Three different terms: solar constant, that's how much heat's coming from the sun, and that varies. Anytime we have a solar flare or there's changes in our wobble of our orbit, we're going to have a different solar constant, but it's relatively constant, hence they call it constant, solar constant. The energy reflected back to space, that's your albedo. So if you've got a big ice flow, it's going to reflect way more energy back into space than if you have warm, dark ocean water. So this top would reflect more heat back. In fact, one of the ways to fix, quote unquote fix, or mitigate climate change is to start painting all of our roofs white so that they'll reflect more heat back. If you were living in the North Pole, you would maybe have all dark roofs, right? Almost all of these concepts can be applied to something practically. And then of course we've got the energy retained in the atmosphere, and that's called the greenhouse effect, which we'll talk about. If there was no energy transfer, the poles would be 25 degrees Celsius cooler and the equator would be 14 degrees Celsius warmer, and we'd have a very different planet. So we're going to talk a little bit about density because that makes the ocean go round. Density is, if you've ever eaten a fruit cake, you know it's the amount of fruit that's jammed into that cake along with rum and flour, and it gets denser and denser and it's heavier, right? So density is the ratio of the mass to volume. So how much something weighs in a set amount of volume. That's what density is. The density of pure water is about 1,000 kilograms per meter cubed. So water is, we're very fortunate that water, 1 milliliter water, 1 cc weighs 1 gram, pure water. So it's a 1 to 1 to 1 ratio. Most substances expand when they're heated and contract and become more dense when they're cool, except for which substance? Water, exactly. As water raises from 0 to 3.98 degrees Celsius, it scrunches together a bit, scientific word, and its density goes up slightly. This factor protects life at the bottom of ponds where denser, slightly water-warm water hangs out and prevents ponds from freezing down to the very bottom. It's pretty rare for ponds to actually freeze solid. It can happen occasionally. A lot of times it's also because of the organic matter at the bottom, but even a shallow 3-foot pond, this is saving goldfish all over the world, there'll be a little bit of liquid water there at the bottom. And you're also, as that ice starts forming, it's going to be fresher and all of the particles in the water are going to stay in the liquid state. It's basically condensing or removing the salts will stay in the liquid part. So in a pinch, even if you have salt water, some of the parts of ice are actually going to be pretty fresh. Pure water freezes at 0 degrees Celsius and expands and has a density of 917 kilograms per meter cubed. That's a big change, which is why ice floats. I'm going to show this today, and then we'll talk about this a lot more next week. So this is a pycnocline. So this is the change in density with depth in the ocean. Oceanographers always look at something up here on this axis versus the y-axis is almost always depth, right? Because you're looking at the depth of the ocean. So salt water is denser than pure water because of the salts. The density of pure water is 1,000 kilograms per meter cubed. Ocean water is more dense because of the salt in it. The density of ocean water at the sea surface is about 1027. So pure water would be way over here, right? At 1.000. Salt water would be at 1.027. Ocean water gets more dense as the temperature goes down. So this is getting more dense because everything's being shoved together. So the colder the water, the more dense it is. Now these are little tiny differences in volume and density, but these little tiny differences in density, as we learn when we talk about thermal haline circulation, cause water to go all the way from Labrador all the way down to the Pacific, all the way down and around continents into the Pacific. It doesn't take much. Yep?
Does the angle of the hydrogen bonds hit a minimum at some point?
Yes, the 104.5 is the minimum. Yeah, they can't, and they're really strong. It's very hard to actually, lower that angle. Because that charge is so strong. It seems small with the electrons, but for that small a molecule, it's a lot of electromagnetic radiation and charge. So water can get denser if it's colder and if it's saltier. And this is something I do in classrooms all the time on Nantucket. I'll go take warm water, hot water, fresh water, salt water, and you add different colored dyes and you take in the classroom and you make a huge mess with food coloring all over it. But you're showing that the cold water is going to sit on the bottom and the saltier water is going to sit on the bottom. If you go into a harbor, you're going to have fresh water floating on top of salt water. So after all those rains the other day, we probably changed our salinity in the harbor by about 2 parts per thousand, and most of that water would be floating on top. If you took my salinity meter, which I'll pull out here in a bit, and lowered it, you'd see fresh water and then salt, salt, salt. So it actually floats that on top. If you go into a river or an estuarine system, you're going to have fresh salt water or fresh water flowing out and the salt water flowing under. That's called a salt wedge. So the density differences, it seems like tiny differences, but they're extremely obvious. And if you're in the Hudson River, let's say, you can go 20, 30 miles up, you can go 70 miles up the Hudson River, past New York, up toward, past George Washington Bridge, you're going to find fresh water coming down from the rains, and you're going to find a salt wedge from the ocean moving all the way up. And if you had the salinity meter again, it'd be 0.00015 at the very bottom. It'd be very salty because that salt water is sneaking up there. Another common question and a common property of water is its optical transparency. It's really good that water is so transparent because otherwise things couldn't photosynthesize in water. So it allows light to penetrate to pretty deep, decent depths. The reason water is blue is because blue is the last wavelength in the prism that white light coming from the sun comes through a series of different wavelengths. Red is the first wavelength that's absorbed, then yellow, then green, and then blue. Most photosynthesizers are using red and yellow light to photosynthesize with just a few things using green light. At this depth, there's nothing in the light spectrum they can use, so if you had algae living right here, it's basically just making enough food to stay alive. But the reason why the ocean's blue and the sky is blue is because blue is the last thing to be absorbed. So now you can answer your grandkids' question instead of saying, just go ask your mother. If you guys have, of course, been snorkeling or what, you can see how quickly that light is absorbed. So you don't have to go down that deep to get out of the photic zone. And we'll talk about that quite a bit more when we talk about phytoplankton. But that light penetration controls, obviously, a large amount of what happens in the ocean. Things can only photosynthesize where they're getting light. And this is why it's so important to have fewer particles or no algae blooms in the harbor, because the eelgrass is stuck on the bottom. So if it's getting shaded out or there's a lot of particles, that it's not going to be able to photosynthesize. So this is a little remedial, but it's helpful. Seawater is salt water. For every 1,000 grams of seawater, there are 965 grams of water hanging out being polar, and 35 grams of dissolved material that we call salt. And nowadays we pay a lot of money for this salt. Traditionally, we think of salt as all that is left when seawater is evaporated. Of that, 86% is sodium chloride, so table salt. The other 14% contains potassium, magnesium, manganese, selenium, sulfur, all kinds of other elements. If we took all the world's ocean and evaporated it, it would cover the entire surface of the globe to a depth of 150 feet. There's actually a lot of salt in the ocean. Salt to a chemist, and believe me or not, we've only got 3 or 4 more chemistry slides. As a chemist, I'm not going to dump 19 years of chemistry on you. But when I think of a salt, I just think of a cation and an anion. I just think of an ionic compound, basically a metal and a non-metal. So I don't think of sodium chloride. So here is the chlorine part, Cl minus. Here's the sodium, Na+. Sodium becomes, if you split sodium chloride up, if water's in business, it's going to separate out that salt. It's going to dissolve it. It's going to make both of these ionic, which means they're going to be all by their lonesome. Sodium's going to have a positive charge, chlorine's negative. Anion, cation. So here's your calcium, your magnesium, potassium, and other things. So there's actually over 100 different elements in salt water. But these are the top 6. Sulfate is a big, important ion. Here's another way to look at that. Here's your chloride, your sodium, sulfate. Everything else is in trace levels. But you've got strontium, barium. It always cracks me up because people bring water to me and go, oh my God, there's strontium. And I'm like, I hope so. Because it was there to begin with, and if it's not there, then something's happened. When chemists look at salt water, we're looking, most of the time, we're like, yeah, there's sodium and chloride. Most of us spend our whole lives down here in the weeds looking at things in the part per trillion or part per billion or maybe part per million levels. So this is where things change and can affect things. Calcium, potassium, magnesium, sulfate. Most of the earth is pretty well buffered, and so we'll learn that salt doesn't change that much around the planet, even with all the icebergs melting. Yep?
The rest of those are elements. Sulfate's a compound, right?
Sulfate is an anion, or an ion in this case. So a compound's usually not charged, but it is sulfate's SO4 minus, so it's sulfur plus oxygen. You can have an anion that's two different elements. So a compound is a combination of two elements, but a lot of times when people use the word compound, they're not thinking charged. So the only difference is this is two elements forming a charged compound. So that'd be the whole part of that. Let's see. Oh, and this is all concentrations in parts per trillion, and we'll talk about that more in just a second. But here is the breakdown of all of this. No matter where you go on the globe, if you take some salt water and divide it up into these things, you're going to see most of these same constituents. So where does this salt come from? Remember last week we talked about the beginning of the earth and the ground that was formed and the rain that was falling on the ground, on this virgin ground that no rain had ever fallen upon. And that's when it started leaching out all of these elements, these compounds, these ions. So salt comes from the weathering of the continents, from hydrothermal vents, and from submarine volcanoes, and we'll talk about those. So these volcanoes are going to blow. You're going to have moisture up here. The moisture is going to extract out that sulfur. That makes sense now that there's a lot of sulfur, you know, because there's a lot of sulfur in volcanoes. There's a lot of magnesium, there's a lot of manganese, a lot of bromide. So that's going to run off from this area and it's going to extract the salts. So there's a whole salt budget and it all cycles. Salinity, and I brought a salinity meter with me today. These poor little meters get used, a couple hundred times a day in the summertime. So I brought a salinity meter which uses conductivity to measure the concentration of salt in seawater. Salinity is the saltiness. The measure of this, back in Darwin's day, you just would grab buckets of water, you would heat them on the deck, and you would actually weigh the amount of salt left over. That's how they found out the percentage of salt that was in salt water. And it's really pretty accurate. That's another thing we do with school kids, and it's pretty crazy how much salt. If you just go take a glass and fill it up out in the harbor, bring it to your house, put it somewhere where the husband or cats can't get to it, and just leave it sitting there and wait for a couple of weeks as it evaporates, especially in the winter, you'll be amazed at how much salt is in there. Salinity is actually dimensionless because it's the amount of weight in weight. So it's dissolved material in grams in 1 kilogram of seawater, so it has no units. Seawater typically has a salinity around 35 grams per kilogram or 35 parts per thousand. Around the world, it's about 33.8 parts per thousand. And it's been determined a variety of ways. When we do this in classes, we'll do it with density, and we'll use a hygrometer to look at the density of salts, and that'll be one way you can measure salt. And salinity, we'll use the amount that dissolves out, we'll use the conductivity, and we'll use refraction. So a refractometer will show the refraction of the water. And here's a link that will be in your Dropbox thing that tells you more. Very few people understand, but most of the ocean is all about the same stuff. It's all in this single, this is a special type of diagram that shows the potential temperature and the salinity, and most of the world's ocean is all in the same area. This is just some variety. Exceptions are the Mediterranean Sea is 38 to 40 parts per thousand, and the Baltic, which is 8 to 10 parts per thousand. And one of the funnest things to talk to about kids when you're talking about density is, of course, if you guys have swam in both freshwater and saltwater, you're buoyed up, of course, in saltwater because it's denser than freshwater. So if you were in the Mediterranean, it would be even easier to swim because it's even denser because it's saltier, right? How many people here have swum in the Mediterranean? Probably a lot. That's about 25% of the people. Was it easier? Did it feel easier, or is it harder because, you know, some people are used to being able to just push through X amount of water, so I can't swim, so it would be hard either way for me. I don't think I'd be worrying too much about the saltiness. Yes, and I know it's funny and ironic that an oceanographer can't swim. I just learned Matticat Millie couldn't either. I'm like, all right then. All right, if she couldn't swim, I'm never gonna worry about it again. Here's showing a lot of the different types of salt water in the world. Regular saline water is what we think of when we think of the ocean. Brinish water is what you would think of in a great salt pond in an area that's very high evaporation. And of course the Mediterranean and the Dead Sea and the Red Sea are very briny, which means more than just saline. Brackish water is a term all of you all know, and that's everything between 0.5 and 30 parts per thousand. There's a lot of variety. You know, our whole harbor is 30 parts per thousand usually, so I wouldn't necessarily call it brackish. I usually think of brackish as being about 2 parts per thousand to about 22. And then fresh water is anything less than about 0.5 parts per thousand. And most of our groundwater on the island is very fresh, though there's areas in Madaket where it's up to 0.5. Very few places underground or in our ponds are above 0.5. We can taste salinity usually up to about 1/2 part per thousand. You can't taste it if it's below that, or most people can't unless you're superhuman salt tasting. Measuring salinity, I talked a little bit about this, but original oceanographers just waited. Now we measure the ratio of the electrical conductivity. So this is one of the funnest facts I tell my students, and it kind of freaks them out. When you're standing in water, you're going to get electrocuted because of the salts are going to be what carries the conductivity. Water is very polar, and it doesn't really like to carry electricity. So we measure how clean water is by looking at the resistance of water. So if you come to my lab and you look at my super clean water, it's very resistant water. It doesn't like to conduct electricity because it hasn't got very many particles in it. So those particles are handing off that electrical charge. So theoretically, in another world, you could, if you're standing in perfectly clean water and it was 0 particles, it would be almost impossible to be electrocuted, which usually blows their little minds. I'm like, do not go do this, because this isn't a perfect world, but it's the particles that are carrying the charge. They're carrying in this case, the electrical charge. So we measure salinity by measuring how strong that charge is. Makes sense, right? So that's going to be a 1-to-1 relationship with the ability of it to carry electricity, so we can use a simple conductance meter to measure salinity. And I brought one of those here today, and they're actually very stable. Units of salinity are called PSUs, or practical salinity units, and that's a unitless number. The mixing time of the ocean, in the deep Atlantic, it's 300 years. In the deep Pacific, it's 600 years. And we'll talk a little bit about this, but the Atlantic is a younger ocean, it's smaller, the mixing time's much lower, and there's all kinds of water being created up in the Labrador Sea. The Pacific is very big, it's old, and it takes 600 years, so the average mixing time for a particle to travel through the Pacific, you could even relate this in some ways like with Fukushima. We are looking to see how those particles of radiation are going from Japan throughout the entire ocean. So this might actually get evaluated because we have a tracer. Back in the old days, they'd use things like rubber duckies, but rubber duckies, of course, are pushed by wind and currents, blah, blah, blah. But if you're looking at a chemical, something or a dye or something like that, the mixing time is how long it takes for it to stay in that basin. The British Challenger expedition traveled 70,000 nautical miles and took hundreds of samples from the seafloor through the water column. They probably did, probably 60,000 of those were literally plates of salt water that they were evaporating. Fun times. Just as exciting now on a saltwater when you're doing a research cruise. Often you're staring at water evaporating. But that's, if you were staring at water and it wasn't evaporating, now that would be exciting. That would be a problem, though. So here's sea surface salinity worldwide, and it makes sense, right? It's a little bit lower salinity everywhere there's a big river. This is higher salinity are the warm colors. The cooler colors are low salinity, so up by the poles, it's going to be very fresh for being relative, like 33. And then around the equator, anywhere it's really hot, it's going to be saltier because it's evaporating. So this is called a sea surface salinity map. One of the ways that we look at things like El Nino are both temperature and salinity. So if we see the salinity going up, we know the temperature is going up, and that's how we can track. It's another way to track temperature anomalies. So here's a famous Nantucket picture. You guys probably all saw the slush wave. You might have heard me on NPR talking about the world's worst margarita. The NPR called me, and I thought it was WCII, and it was actually the NPR. And they had asked me, as the oceanographer closest to Jonathan, this is his photo, by the way, and he's an amazing photographer. they called and said, oh, you're an oceanographer, explain this picture to me. So I was explaining it to them, and they go, well, how would it taste? I go, okay, I don't really look at ocean waves and go, oh, that looks tasty, I think I'll take it. I go, not that I'd ever do it, but I guess if you took it, I said the ice on top would be very fresh, because as water freezes, it becomes saltier underneath, but the water that freezes out is actually fresh water. So I said if you extracted those little ice cubes, they'd be pretty fresh. I go, the rest of it would be the world's worst tequila. It'd be all salt and no margarita. Or no, worst margarita, all salt, no tequila. And that went around the world. I thought I was talking to the folks over in Woods Hole. And the next morning I got phone calls from London and from California, and they're like, you were just on the radio. I'm like, oh, come on. And they're like, nope, I was listening to NPR. So note to self, if you think someone's calling you and they're local, they're not always. But the cool thing about living here on Nantucket, there's lots of cool things, but we get to see all these different forms of ice, right? A lot of people don't get to see this because we do have really intense periods of cooling, like yesterday when you guys were outside. Remember how cold it was? Because it was so windy. So it's 30 degrees, but it's 30-mile-per-hour wind. So we build up these chances to form some pretty cool ice because we're blowing a lot of wind across a liquid and we're pulling off that latent heat. So, and the sensible heat. So the forms of ice we can see in the ocean here go from something that looks kind of greasy, then you'll get frazzle ice, and frazzle ice is kind of that ice that looks like, you know, it's very sharp and jagged, and it looks kind of like it's just getting started, and it is. Then you'll get slush. The slush tells us that this is much colder situation. Then you're going to get pancake ice. Do you guys remember the pancake ice we had in 2005 out in the harbor? It's literally curled on the edges. It's something you normally would see in the Antarctic. It's very weird, and it looks like little pancakes. So I remember being on the big ferry, trudging through all this pancake ice. Then you're going to go into ice flows. So we'll often get these ice flows. They'll grind themselves up on our when we're walking around the harbor. So these are all things we can see. Seawater can be compressed a little bit under pressure, but pressure doesn't really change the density as much as you would think. It does change it a little bit. We can measure it, but it's not critical. This is just called IsoVAR. This is lines of equal density at different temperatures and different salinities. So this is one density of 1.024, which you could experience at 14 degrees Celsius or at a salinity of 36. So it's just showing how temperature and salinity are relative and showing how that affects density. We put that onto a IsoVAR graph, and this is what oceanographers look at all the time. Here's your temperature, here's your salinity. Most of the world's ocean is right here. See, so this is all the possibilities, and 90% of the ocean is all the same. Super well buffered right in that little bar. Very last thought on seawater is not just innocent, you know, salt floating around devoid of life. When we go sample seawater, we use, this is called a rosette. I've spent hundreds of thousands of hours in close personal proximity to this rosette. So the exciting life of an oceanographer is you take this, you put it on a crane, you lower it down to 2.5 miles, right? The average depth of the ocean, which takes about 3 hours. These are all triggered by computer. They're open. So at each depth, they snap shut and they collapse and capture the salt water in these little Niskin bottles. So each of them are triggered at a different depth, and you wait about 6 hours, and it gets up on deck, and then everybody crowds around here, and basically we call it milking the cow. We all take this 20 liters of water, goes to usually about 30 scientists. So that water is truly more precious than gold because it represents that day, that time, and everything that was happening in the water column. But it's, you know, 6 hours of boredom. Now you can see this person right here is taking water off of there, out of that Niskin. So is this person. And then you go back to the lab on the boat and you look at it for phytoplankton, for fossil, you know, for microscopic creatures, for pesticides, for all kinds of contaminants, for radionuclides. But this all starts here. So the ocean is a soup full of dead plants and animals and, you know, bits of octopus, and, you know, it's not, you know, when you start looking at it, there's all kinds of things in it. It's truly like a soup. So now we're going to switch gears. We've talked about the ocean's watery world. Good, it's 6 o'clock now. Oh my gosh, 6 o'clock. Okay, kumbaya. So we're going to go through as much of this as we can get through. We're going to talk about the ocean floor. And here's an example of the ocean floor, an idealized floor. Here's your continent, your continental shelf, your slope, your submarine canyon, your continental rise, and I'll cover all this at length. Mid-ocean ridge, abyssal plain, it's one of my favorite words in oceanography, abyssal plain, it sounds like. And the 4 horsemen of the apocalypse were riding across the abyssal plain. And these terms all came from, these early, forms of the Darwin and the Beagle and all of these ships out there for years, so it probably did feel pretty abyssal to them. Abyssal hills, we'll talk about that, and then we've got a big trench and a volcanic island. So we'll talk about how this forms. So here's the ocean greatly exaggerated in cross-section. Here again, so we're looking in profile. Here's the continental shelf, the continental slope, which is not that, it's not like you're going to fall off on it. Though we do have, there are avalanches that occur all the time off the slope and shelf that dig out big canyons. We have the continental rise, and this is just the area where the change in elevation is not very great. That's why they call it the continental rise. Here's the abyssal plain. So this would, in reality, you would stretch this across and it would run to, past Center Street and all the way to the harbor. So this is all squished in. Your oceanic trench, your volcanic island, and your funky chicken head looking submarine ridge. Continental drift, we talked a little bit about this the other day. It was proposed by Alfred Wegener. Originally, we all lived on a supercontinent. People, when he first proposed this, thought he was completely crazy, completely nuts. Wegener pointed to existing evidence from mountain ranges and fossils, and we'll talk about that. Most geologists did not support continental drift. He was considered to be a complete ding-dong. So, let's see if I missed something there. Nope. So pieces of the Earth's surface look like they once fit together. There's overlap, so people started looking at the globe, which I had a globe last week. I didn't bring it today because I had that for my show and tell. But they said, hey, this looks like this fits here, and this looks, it's like, okay. That doesn't take a rocket scientist to figure that out. But it took good maps to figure that out. So then people go, hey, there's the same fossils over here and over here. There's the same creatures, and they're not flying creatures. So we're finding fossilized, on their feet, flying creatures on different continents. And fossil ferns were found on all of these southern land masses. So the same kind of fern was found on all of these continents, including Antarctica. So they're like, that doesn't make sense. Why would a fern be in all the same area? So then we started, I'm going to jump ahead to the Earth's layer, and then we're going to come back to that. So some smart people go, hey, there's a difference in the Earth. It's not just all the same kind of gumball. There's different changes in density. Going back to our favorite density, Earth is density stratified. Earthquakes generate seismic waves that are measured by seismographs. So the first time that people, and all of this theory started in 1917, people laughed at him for about 30 or 40 years, and it was like 1950, 1960, 1970, actually in my lifetime before this theory. And earthquakes were one of the things that started proving to people that Pangea and continental drift existed. So bear with me, it'll take me a second to explain this. If the Earth was just homogeneous, all the same, and there was an earthquake here, it would just go straight through the Earth at a set number of in a set amount of time. Just the speed of sound through solid material would be a straight line. If there was a density that increased uniformly, it would go toward the center, but it would bend in those kind of angles. But if we have an actual gumball Earth with a different center, then you're going to get reflection and refraction, and you're going to have some of these waves actually bounce back to us, and some that never go through the center. So there's an earthquake here, it can be heard there, but not there. And it took a lot of scientists working with seismographs, and that's all they're doing is watching a little pin, right? And they're looking at movement, and they're listening to hydrophones. So they get kind of bored, just like radio ham operators used to, and they call each other, right, all over the planet, go, hey, we just had an earthquake, did you hear it? And this guy over here, a girl over here is like, no, what do you mean? And all these other people are like, well, we just had it, it's on our machines. People are like, why didn't you see it, right? So this is literally, it's just observational, and this person's like, first he would try to fix his machine, right? And then he'd get a new machine. You know, there'd be a million things you'd do before you think, oh, the inside of the Earth is layered and it bounced off of, you know, this is, you know, Morlocks and stuff that were, people thought the inside of the Earth, people thought there were a whole continent on the inside of the Earth, there were an entire different land. They certainly didn't think that it was solid iron and then a liquid molten center, you know, like a lava cake. People didn't think that's how the Earth was, but it was. So each of these layers has a different property. Our continental crust is made of mainly granite. It's pretty, it's 2.7 grams per centimeter cube. So this is its chemical properties. It's pretty light. Oceanic crust is mainly basalt. It's 2.9 grams per centimeter cube. Most rocks are about 2.5 to 2.7 grams per centimeter cube. You can actually, after a while, feel that. Someone can hand you a rock and you can go, oh, that's a little denser than another rock, right? When you pick up rocks on the beach, you can go, and that's telling you there's more iron in it, maybe more nickel. You know, you guys know all this stuff. I really don't need to tell you any of it. The mantle, if you swim down to the mantle and get a hold of that, that's composed of silicon, oxygen, iron, and magnesium. That's one of the big layers on the inside of the Earth. Its density is very dense, 4.5 grams per centimeter cubed, and the inner core is 13 grams per centimeter cubed and is almost all iron. So each of these layers, I'm probably going to, you've got the lithosphere, which is the very top layer that's floating and it's rigid. And then you've got this asthenosphere, and we'll show you a couple of pictures of this. It's hot and it's partially melted layer. When people first started looking at continental drifts, they thought, oh, are these plates just floating around loose? And no, they're actually sitting on this Play-Doh layer that's the asthenosphere that flows very slowly, like a glacier. The mantle is very dense. It also flows. The outer core is very dense, very viscous, extremely hot. The inner core is solid, very dense, and extremely hot. So a lot of people don't realize that the inner core of the Earth is actually solid. It's not liquid. You would think, and that's how we started thinking about these different density layers, right? We could do a whole class on this. I'm kind of going through it fast, but it'll be helpful. You'll understand. Ocean crust basalt, continental crust granite, mantle, oxygen, iron, manganese, and silicon. And remember when we were talking about the Big Bang and how the Earth formed and gravity and how different heavier elements started migrating to the center of the Earth differentiated itself. All the lighter stuff, it's like a balloon. All the lighter stuff went to the outside of the crust. And the heavier, denser elements went down to the center. Does that make sense? So the outer and inner core mainly consist of iron and nickel. If we were in need of a lot of iron and nickel, we would need to figure out a way to somehow mine the inner and outer core. The mantle is where we produce more earth. In volcanoes, it's coming from here, and it's oxygen, iron, magnesium, and silicon, which are the largest portion of the Earth is made of these elements. These are all pretty lightweight elements. Remember we were talking about hydrogen and helium get together and they form a heavier element. We were talking about the formation of the Earth and all the stars. Here's a picture of that inner core, outer core. This is obviously a drawing. Here is that lithosphere right there. Here's the asthenosphere, which is deformable and capable of moving. So these are the plates that are going to be in the lithosphere and they're carried along in the asthenosphere. And here's the lower mantle, which has to have a place to connect up here to create a volcano. So all of this information started getting geologists convinced that Wegener might not have been the crazy person they thought. Seismographs revealed the pattern of volcanoes and earthquakes, especially around the Pacific Ring of Fire. So they started seeing things happen in certain areas of the Earth and going, that's strange. I wonder why that is. Radioactive dating showed the rocks revealed a surprisingly young ocean crust. So when we took grab samples from the Beagle, which took hundreds of hours to get up to the surface, they would radio date that and go, this is only 20 million years old or 20,000 years old. They're like, why is this rock over here 400 million years old? And that's when we started thinking, ocean's young. I'm like, well, why is the ocean young? And you'll find out why. Echo sounders revealed the shape of the mid-ocean ridge. Remember when we were talking last week about laying the cable across the mid-ocean ridge and they went, oh, it's 4,000 feet, 4,000 feet, 2,000 feet. And you're like, what the? And once again, you check is everything broken? Or is everyone drunk? Why are it's all of a sudden we have, because we thought the ocean was flat, nothing going on, certainly no mountains. So, and then seismic studies indicated the plasticity of the inner upper mantle. It showed those bouncy signals and showed that there was a density difference that we couldn't explain. So the breakthrough from seafloor spreading to plate tectonics, we determined Earth's outer layer is divided into these plates. They're floating on the asthenosphere. The movement is transmitted by convection currents. So if you get a pot of water on a stove moving, you're going to start creating convection currents in the asthenosphere that's going to create seafloor spreading. Anywhere it's hot, you're going to get movement away from that. Plates are subducted into the mantle at subduction zones. So the plates are created in one area, and then they go and they get subducted down, and that's where you don't want to live, is because that's where all the earthquakes are happening. Most of you guys know how convection works. You turn this on, it gets hot, somebody usually gets burned. This cold soup starts sinking. Hot soup's up here. If you had a really cool temperature meter, oops, sorry, don't mean to blind you. If you had a temperature meter, you would be able to see that this is hotter here, this is colder. As this rises, it's actually going to set up a current. And that's exactly what happens in the earth and in the ocean and anything like that. So the seafloor spreading drives the plate tectonics. Here's the spreading center, right here. Here's the mid-ocean ridge. Here's the ocean crust, mainly made of basalt. Here's the mantle, a lot of oxygen, silicon, magnesium. It's going to start getting hot from the even hotter area underneath. It's under pressure. It rises. It creates this new crust. This crust starts moving, and it heads over to this continental crust, which is cool, and it sinks below it because this is really light, right? So this sinks down, and as it sinks down, it pulls some water and stuff down it, and it gets away from the spreading center, and it causes these little hot areas that cause volcanoes. That's why you have all these mountain ridges right along areas of California. Here's the whole system for the whole planet. Here's your hot spot like an island. Here's your lithosphere and your continental crust. Here's a convection cell. Here's another one. Here's that spreading seafloor. And here's the continental ridges, right? And each of those are created. So once you start learning about this and looking at the planet, you're like, I totally understand why the Rift Valley is in the, in Africa, why this looks like that. The plates are being created here on the mid-ocean ridge, and then here's where all the earthquakes are, and that's because those are subduction zones or areas where two plates are colliding. And we'll talk about the plates. 6:13. I've probably got 30 more slides. Obviously, I'm not going to do those in 15 minutes. I'll do about 10 more slides and then stop for questions. Does that sound good? Okay. Here's another example of the plates. And this picture actually shows speed and movement. So if you study this, you can actually determine how strong an earthquake is going to be and how fast things are moving. They call this the baseball. When you look at a baseball and you see that line around, that's what the term is for the mid-ocean ridges, is the baseball stitching, the baseball earth. So the mid-ocean ridge is the longest continuous mountain range on the planet, and it's at a depth of 2.5 to 4 miles. And it's all the way around here. So this is baby Earth being created. Isn't it cute? All right here. It's we'll talk about mid-ocean ridges and vents. There's creatures that live right there. So there's 3 types of plate boundaries: divergent, going away; convergent, coming together; or transform boundary, where you have shear, where one area is going opposite of another. And when you look at earthquakes, all of them are caused by one of these, well, out of 2 of these things. Here's this plate, 2 different plates. This overlap is where you have a convergent boundary. Here's a slip fault or a transfer fault, or a transfer boundary, and this gap is where they're diverging. So 2 plates are escaping each other. There's going to be a new crust created there, and that's divergent. Convergence means 2 of them are coming together, and they're typically one's going to go under the other. Things like the Andes, all of that are created by one plate going under another. Here's another example: magma, ocean crust, continent, spreading, ocean floor. So remember, Pangea again, everybody was all together. And then continents started getting pushed across. They were being moved by this magma and by this conveyor belt system.
Sarah?
Yep.
If there was when you had Pangea.
Pardon?
When there was Pangea, there was no ocean between the continents. So how did they get pushed apart if this ocean spreading at one time?
it started forming right in between those two. So you still had heat underneath that and convection. So you probably had a change there in the density of the Earth that started forcing apart. So you had these plates where, when you look at a ball, there's no way that the skin of a ball is going to be intact all the way around. You're going to have these jagged edges. So in two areas where there's a jagged edge, that's where heat could escape and start forming. So it's probably something that simple. And I've got a little animation about Pangea, which might help us, but it's a really good question. Here's the divergent boundary, convergent boundary, which is destructive. Here's our divergent, which is creative, right? Constructive. And here's your transform boundary. The problems in California are a combination of really all of those. Here's the area where you've got San Andreas Fault. You've got one plate moving north, one plate moving south. That's why it keeps getting those slip earthquakes that are like doo-doo-doo, and you get this slip, and those are harder to predict. Here is the Azca plate over off of South America. It's converging right there. Here's the divergent plate, and here's all the plate lines, and showing exactly what it looks like. And you will get an ocean trench right there, right next to that. It's another example. Here's a rift valley, and here's the growing Atlantic. So you've got a valley that starts like this. You've got magma coming up, volcanic activity. So you're going to start warping that. So just the heat is going to cause this to start forming and split it apart. It could almost unzip it too. I would assume that there'd have to be some kind of anomaly there to get it going. Ocean basins form at divergent plate boundaries. So that boundary probably always existed in that location. And this is what it looks like if you're measuring it from space. So here's Pangea. This is stage 1. Everybody's all together. Stage 2, everything starts moving apart. This is the late Triassic, 180 million years ago. MA is million years ago. So minus 210 million years ago is Triassic. Everybody's all here together, and a lot of land mass is in the south. That's why the dinosaurs all were pretty warm. Stage 3, you're moving farther apart. This is forming, this ocean's forming. You're still not forming the Atlantic until the Cretaceous era when you start forming the Atlantic. And then here to present is the mid-ocean range. And these guys are all still moving, so a lot of students ask if they're all going to huddle over on the other side of the planet. And I think there are some animations that show the natural progression, because like we tend to do, a lot of times we think, oh, we're at a stable part, but we probably are at a point where some things are going to start getting closer to others. Okay, 2 more minutes and then we'll stop on this one. This is talking about different types of island arcs. I'm actually going to slip over that. This is showing this plate going down. This is dragging basalt down, and it's mixing with the mantle, and this is all pretty pyroclastic and pretty violent, and this is causing the Andes volcanoes in South America. This is the Peru-Chile trench, and here's your continental interior. So when you think about this, is actually scraping as it goes down, and then it's getting scraped right there, and it's causing all of this different temperature elements to mix together and get heated, superheated, and then it's going to go through these different types of magma tunnels and explode out. It's another subduction zone. The island arcs are just a hot spot underneath the planet. In this case, Japan is a very strong zone for creating. Here's all of the different earthquakes off of. So people, I mean, they're probably not the best place to put a nuclear power plant. That's just me, but would be like, oh, look, they're most earthquakes known to, you know, beautiful mountains and great skiing, and let's put a, so. And when you think about it, a lot of these plans were made before people believed Wegener and believed plate tectonics. So this is something that to us, we're like, oh, it's always existed, but back then, like I said, people thought he was nuts. Here's showing that California obviously is very, very interesting. Here's all the different faults. There's hundreds of faults occurring down here, and this is that zigzag shape. Here are the transform faults. So there's several different plates coming in together. There's this big trench here, huge trench right along there. So you've got your North American plate and your Pacific plate that are both fighting, and they don't like each other, as we know. This is looking at magnetic fields. So this is what I was talking to you last week about the magnetism that's measured by iron particles that match each other on either side in this flip-flopping pole that showed that on either side of a growing new ocean floor, we had rock that matched each other in age. Let me see if that's, and here's the age of the ocean floor, and I'll stop it on this one. So here's talking how this is late Jurassic, the oldest, and then the youngest is the Pleistocene, which is to now, up to the Anthropocene. And you can see this is the youngest ocean floor. So we started going around and radio dating the ocean floor, and we said, well, obviously there are areas where ocean floor is being created and areas where it's much older. So the subduction areas are where it's getting subducted. See in this area right around Alaska and over in Japan where it's getting subducted down. So that's when you're going to have more earthquakes. And people once again thought this would all be uniform. I don't know, we always think everything is uniform. But then we started taking samples and we're like, this ocean floor is 20 million years old and this is 200 million years old. What's up with that? And it took a lot of little pieces of evidence. I'll stop it there. Next time we'll talk a little bit about how the island chains like Hawaii form, but I wanted to give you guys a couple of minutes for questions if you'd like. Yes, Annie?
I was wondering if anyone figured out why the poles flip around the trench.
There are people that have figured why the magnetism trenches. Part of it is just how the wobble of the Earth and then where the sun is, but that's something I should look up. Because there's a reason for that magnetism. A lot of it has to do too with that liquid earth inside, and you've got a ball bearing basically in the dead center. That's all the nickel.
So
That's
its charge.
It basically changes from being, yeah, it doesn't go from like 180, but it might go from a polarity of positive 20 to minus 40. So it was enough where if you were holding a compass back then, north would not be north. Your compass would flip, magnetic north would have actually moved. Isn't that bizarre? That's why I'm like, I can't believe there was a planet where compasses worked differently. There's certain things in your life that you think are always been the same. But you know, talk to the people in Pangea, they're like, well, I thought we were all one big happy family down, you know, with Antarctica somewhere where it's warm and all the dinosaurs were, you know, in jungles. And then we separated out and floated closer to higher latitudes and got much colder. So the Earth's changed a lot over time. And once we start talking about atmospheric circulation and the formation of these big oceans and the circulation around the oceans, you'll see why the climate is the way it is. Any more questions? Yep.
Could you address why the El Nino this year is so strong and why it is where it is off the Pacific coast? It's sort of what you see happening.
Yeah, we're going to have a class toward the end about it, but there's a sloshing in the ocean. It's based on temperature and prevailing winds and the spin of the Earth and centripetal force. So it's always, the ocean is a big basin and it sloshes back and forth. So on one side of the ocean, it's a little higher than the other. Temperature changes the density. So right off of Chile, you've got all that upwelling. So you've got hot water moving off and you've got cold water coming up bringing nutrients. What happens is a bunch of water gets piled up on the Japanese side, it gets pushed back over, and that dampens and shuts off that upwelling. So it actually pushes that water down, kills the fishery, and starts trying to redistribute that heat. So that is basically a thermostat reset that's happening with El Nino, and it all makes sense with physics and heat distribution. Once there's X amount of heat, the problem is we're setting this up more frequently because we're warming the surface of the sea. And we're warming our atmosphere. We're increasing the greenhouse effect. So remember I said half the ocean and the atmosphere were 50-50 on heat redistribution. We're fouling both of those up and we're introducing more heat into the atmosphere. We're taking dinosaurs and throwing that carbon up into the atmosphere. So we're speeding up this conveyor belt. So to go back to El Nino, what's happening is that's a temperature reset and an oceanic reset that's forcing that down. It's getting bigger each time. It happens every 10 to 13 years because there's more heat in the ocean. That's why we're getting a few more hurricanes. There's just more fuel to the fire. So now the ocean is, you know, 1 to 1.5 degrees Celsius warmer than it was 100 years ago. So as we add heat to the atmosphere, the ocean's trying to help us out and redistribute that heat. But unless we can figure a way to change things drastically, they're just going to get worse. So it's really, there's a whole, we'll have a whole section in the circulation that discusses El Nino and El Nino, La Nina, and that whole circulation, and it's linked to atmospheric circulation. So we'll talk about Hadley cells, because when we've got that heat around the equator, it causes warm air to rise, and you get convection in the atmosphere. So you've got ocean convection, earth convection, atmosphere, they're all connected. It almost looks like the clock at the Whaling Museum, you know, when you have all of these gears. It's the same thing of thinking. When one gear starts moving, the other one's got to go faster too, because they're connected. It's a really good question. It's a bit of a concern with El Nino, and I think that that's going to get a little bit worse. Yep.
Could you talk about whether, or maybe it was a myth, but could you talk about whether the center of the Earth at one time was molten, and how big was it, and when did that happen?
Well, parts of it that when we were looking at the layers, part of the center of the Earth is molten. So when we go back to the very beginning, that outer mantle, and actually the asthenosphere is molten, but it's not super hot. The outer mantle, and I know there's a faster way to do that, but I'm lazy. So this inner core right here is solid, but this is liquid, and this is liquid. So what's funny is everyone always thinks of the Earth as revolving just calmly in its tracks, but this does really act like a ball bearing, and it kind of wobbles around, and it actually has caused the Earth to lurch around a little bit. So, and this has changed, all three of these densities have changed over time. So the density of the Earth, it took a while to set up the core to be 13, remember it's 13 kilograms per meter cubed. It's the most dense here, and it's about 7 here. This rock all the way out here is 2.5.
And how big is the biggest molten part?
Oh, the biggest molten part, let's see if there's, one of these might show it. Let's see, this is not to scale, but here's the crust. Here's the mantle, which is molten, is 2,900 kilometers, so 1,800 miles. The outer core is also molten, and it's another probably 4,000 kilometers. And then the inner core and the inside is probably about 200 kilometers. So 3/4 of the internal part of the Earth is molten. Most of it is. But it's not exactly the same density because those elements separated out. So there's more metals closer in, so it's a different temperature constant too. Does it make sense? Yeah, well, it's interesting because I don't, you know, I'll be going somewhere where we're going to do a lot of drilling and stuff, and I'm from Oklahoma where drilling's a big deal, and obviously we've, you know, the deepest drills, that might be something I'll look up, I mean, might go down that deep. So we have never, you know, tried to go get nickel or, you know, and it would be really interesting because how would you drill it, because your drill would be melting, but. Yes?
You had a slide that showed the different salinity in the ocean.
Yep.
If you could pull that up. It seemed counterintuitive because right where El Nino is was cooler, or was less than the average, was light blue instead of orange.
Yeah, and that makes it's colder because it's upwelling. It's water that's being forced from the bottom. Yep, and we'll have a great class on, actually, see, it'd be good if I have all of them here on my computer, but probably next week we'll be talking about waves and currents and ocean circulation and atmospheric circulation. And I'll make sure and bring up things specifically on El Nino because I kind of like doing the current events. But you can see where that cold water is forced up, and it's a result of ocean circulation and atmospheric circulation. So let's see if I can, I know exactly which, this is the one. This is the sea surface salinity, and it's basically an inverse of sea surface temperature. So you've got the warmest salinity here and here, I mean highest salinity. The lowest salinity is where it's the coldest. And so in these areas right here, and here's where El Nino is, right here is a freshwater area. Part of that's river induced too. If we did a blow up, you could really see the Nile, and you could see the, you can even see the Mississippi River. I did a paper that tracked the Mississippi River 25 kilometers off the coast of New Orleans. So that fresh water goes shooting out. Even in New York, that fresh water goes out about 10 miles. But in here, this is mainly upwelling. So this is where El Nino's getting affected. Mm-hmm.
So that's why there are penguins in the Galapagos. The water's very cold there.
The water's very cold. It's nutrient rich too. These are big fisheries. And it's on the equator. Yes, yes. So there's lots of food. See how warm it is down. This is Antarctica, and the sea surface, the salinity is right around 30, 34, it's not way down in the 33s. You would think that it'd be super fresh, you know, but it's not. And it's pretty, when we look at sea surface temperatures, you're going to see a lot of differences for the Southern Ocean. But this is upwelling areas, and we'll have a whole class probably next week on upwelling. So when you look at the way that water sloshes around, when it leaves the coast, water comes up to fill it. And we can even see it in Massachusetts. You can see areas where water is going one way, and you can see it right off Wisconsin, actually. When you see that steep area, water hits it and then bounces off at a different angle because it's so steep there, but you're going to get upwelling occasionally there because the water, as it goes away, more water is going to come in to fill it, and that's going to come in from at depth. It's not as extreme as off of Chile. Here you can practically see, you know, we can measure stuff from the bottom come shooting up right along in here. People, when this first happened in '86, basically these Chilean fishermen had a very stable fishery, and then one day all the fish started dying. And the temperature changed drastically, and dolphins started dying, and they're like, I don't understand. And there wasn't really any link to pesticides or stuff like that. And that's because we shut off, El Nino shut off that upwelling and basically starved all these creatures. All of the nutrients that feed herring and stuff went away. But that's good for, if you guys have things you want to know specifically about, it's really good to bring up now, because I'll make sure and talk about that next week. You know what I mean? Any other questions? We've got 6:32. I'd like to respect, one more question, then I'll let you guys go and you can come ask me questions here. I'd like to respect your time so you can eat.
I'm interested in salinity in regards to electrolytes. Your body is not water, it's charged particles, so when Gatorade tells you to drink electrolytes, that's not 0.05% salinity. What's that?
Yeah, our blood is actually almost the same as salt water. That's a typical, when they talk about our blood chemistry, it's very similar. It's almost the same salinity as salt water because we use all these electrical currents to conduct, you know, business inside our body. So when you think of electricity and electrolytes and ions, those are carrying, they're doing the work. So it's the fuel inside your body. So yeah, that's when you're drinking electrolytes, it's not quite 30 parts per thousand, and it's not so much sodium chloride, but you're replenishing calcium. Potassium's a big one in our body. Both calcium and potassium, when you guys take beta blockers, you're changing the way that calcium and potassium work in your body. That's why you might need to eat more bananas, for instance, if you're taking a beta blocker. All of this chemistry and all those ions are the ones carrying the good guys and the bad guys through your blood. So when you get really dehydrated, you need to replenish not only the water but your electrolytes too. So that's some of the soup that's doing the good work. So that's a very good point. All of ions is not like pure water is doing that much work. It's acting as a carrier for all these things. I'm glad you reminded me too. I've got a DO meter right here. Sorry, I don't mean to almost pour. And a salinity meter if you guys want to come up and look at them. Kids as young as the junior rangers and stuff use them. They both are very effective. That is just a $200 or $1,000 version of what I was showing before. If on a research vessel, you might have a $20,000 salinity meter because you're looking at little teeny tiny changes in salinity, like 0.001 PSUs. Cool. Any other questions? Did y'all have fun? Yes. Good, good. Good for you for staying awake. Thanks a lot.